Hello, in this session we'll be discussing about quantum mechanical rigid rotor, and we'll confine the we'll discuss the rotational motion in three-dimensional space. Further, we are considering diatomic molecule, and we will not take the diatomic molecule as such, rather we will prefer the center of mass coordinate system. So the model goes like this: in center of mass coordinate system, the rotational motion is transformed to a motion of particle, both the diatomic system is converted into a single center of mass system, and motion of a particle on the surface of sphere with radius r0. So the model, the diatomic molecule behaves as a single point source, and it is rotating at a distance of r0 from the center of a sphere. Now, as there is no hindrance during the rotational motion, there is no external force that is applying, like frictional force or any other residual force that is applying on the system. That's why the potential energy of the system remains constant, and it is set equal to 0. In the rotational motion of two-dimensional space also, we have taken that the potential energy of the system remains constant, and that we have taken that system is equal to 0. Now, why we are studying this rotational motion in three-dimensional space? By understanding the model, the rotational motion of molecule in three-dimensional space, we can find out the bond length of the system, that is r0. The bond length of the system we can find out. So we'll set up the Schrodinger time independent Schrodinger wave equation in spherical polar coordinate. We will not prefer the Cartesian coordinate, rather we will prefer the spherical coordinate system, and we will set up the Schrodinger wave equation in spherical polar coordinate system. We will solve the Schrodinger wave equation, and we will try to extract some meaningful information out of those Schrodinger wave equations, and we will try to relate the energy associated with rotation and the bond length of the diatomic system. So when I set up the Schrodinger wave equation, the Schrodinger wave equation goes like this: minus h bar square over 2 mu r0 square. This radius is another variable in polar coordinate system, but here the radius is taken to be constant, that is r0. 1 over sine theta dou over dou theta sine theta dou over dou theta y, theta and phi. So the function that we have defined here is y, and the eigen function that we have defined is y, and it depends upon two angle variable. The variables are theta and phi. So theta varies from 0 to pi, and phi varies from 0 to 2 pi, plus 1 over sine square theta dou square y over dou phi square is equal to E y, theta and phi. So E is the eigen value of the system, means this is Hamiltonian operator. When Hamiltonian operator is acting on an eigen function, we will get a eigen value corresponding to that eigen function, and that eigen value is the energy of the rotational motion, energy associated with the rotational motion of the system. Again, I am saying the eigen function that we have taken here is represented as y, and it depends upon two variables, that is theta and phi. So this eigen function is generally called, this y theta phi is called spherical harmonics, because it depends upon only two angle variables, that is theta and phi. So the eigen function is y, theta and phi. So what is our aim here? Our aim is to find out eigen function. What are the eigen functions that satisfy this Schrodinger wave equation? First aim is to find out what are the eigen functions or spherical harmonics that satisfy this Schrodinger wave equation. Second aim is to find out what is the associated eigen value. The associated eigenvalue will give us information about the energy of the system or energy of the rotation in three-dimensional space. So before solving this Schrodinger wave equation, we'll do some rearrangements. First, I will take this Ey term to the left hand side, and this second term of left hand side to the right hand side. I'll do one. First, I'll cross multiply. First, I cross multiply 2 mu r0 square in the right hand side. Again, I am repeating, I'll do some rearrangements. First, I'll do cross multiplication of this constant term in left hand side in the right hand side. So what I'll get 2 mu r0 square is E over h bar square. If I take the negative sign as well, so I'll get minus 2 mu r0 square E over h bar square. Now all the terms are constant in nature, so I'll define a new constant, and the new constant is beta. So my RHS becomes beta y theta phi. So I'll take that beta term to the left hand side, and the second term of left hand side to the RHS side, to the right hand side. Now after doing that, I'll multiply both the sides by sine square theta. So if I'll do that, the first term will become sine theta dou over dou theta, because there is a one sine theta term in the denominator. So if I multiply sine square theta, then I'll be getting only sine theta. Similarly, the second term, the RHS has been taken to the left hand side. So there is a beta y was there initially, so beta sine square theta y, the function. Okay, now what is there in RHS side, the right hand side? I have this second term has been taken to the right hand side, so 1 over sine square theta and sine square theta multiplied, so I am left with only dou square y over dou phi square. Okay, so this is the rearranged equation. Now when we look at this equation, we can find out that the left hand side is function of only theta, whereas the right hand side is only a function of what? Phi. Okay, so to solve this kind of expression, or to solve this kind of equation, I'll consider that my spherical harmonic function, that is y theta phi, is product of two independent functions, is product of theta function and is a product of phi function. The phi function is dependent upon the variable phi, and theta function is dependent upon the variable theta, and when you take product of both the theta and phi function, I am getting my spherical harmonic function. So if I substitute this if I substitute my spherical harmonic function in the above expression, so what I'll get, I'll substitute my spherical harmonic function as product of two independent functions. Okay, so for the let's do I'll substitute the spherical harmonic function as product of two independent function. Further, I'll divide throughout the expression, the above expression, by theta and phi function. Okay, again I am repeating, I will substitute the expression for spherical harmonics here, spherical harmonic function here, and I will divide throughout by theta and phi. Now if I substitute here that spherical harmonic function is a product of theta function and phi function. Now the differentiation is taken with respect to theta, so phi function will not be affected and it will come out of the integration. The phi function will come out of the integration. Now I am dividing theta and phi, so phi will come out of the integration, and I am dividing theta and phi function, so phi function in the denominator and numerator will be cancelled out, and I am left with only the theta function, 1 over theta function sine theta. Now this partial derivative is converted to the normal derivative, d over d theta sine theta d over d theta. Now in the spherical harmonic function, it is product of theta and phi, only the theta function is left, phi is taken out, and when I divide throughout by theta and phi function, that phi function is cancelled out, so I am left with this function. The first term of LHS looks like this. Now what about the second term? In second term there is a spherical harmonic function, and I'll substitute it is a product of theta function and phi function. Again I am dividing by theta function and phi function, so I am left with only beta sine square theta. Okay, then what happens in the right hand side? Right hand side is a difference, second order differentiation with respect to phi function, phi. Okay, so when I substitute my spherical harmonics as product of theta and phi function, my theta function will remain unaffected and it will come out of the differentiation, because the partial differentiation is taken with respect to phi, so my theta will come out of the integration, come out of the differentiation, and when I divide by theta and product of theta and phi function, the theta function will cancel out and I will be left with only the phi function. Okay, and here also I can take the normal differentiation, not partial differentiation is not required, because the function is dependent only on the variable phi, so I can take the normal differentiation, d square phi over d phi square. Okay, so the Schrodinger wave equation has been reduced to has been simplified. Now we can see that the equation no longer contains partial derivative. The LHS is a function of theta and RHS is a function of only phi. RHS is a function of only phi. So this type of we have done separation of variable. So this type of rearrangement is called separation of variable concept. The left hand side of the Schrodinger wave equation depends only on theta, and the right hand side of the Schrodinger wave equation depends only on phi function. So therefore both now when this condition can be satisfied, left side depends upon theta, right side depends upon phi, and both are equal. When this condition can be satisfied when both the left hand side and right hand side is equal to another constant. Then only this condition can be satisfied. Again I am repeating, when the theta and phi function will be equal to each other, when both are independently when both sides are are equal to a constant. When left hand side is equal to a constant and right hand side is equal to a constant, then only we can say that left hand side which depends upon theta is equal to right hand side of the function, right hand side of the expression which depend upon phi. So I'll write my left hand side which depends upon a constant, that is ml square, and right hand side that depends upon a function is also ml square, but right hand side there is a negative sign, that's why it is minus ml square. So the constant here is ml square. Okay, so the left hand side is is equal to a constant, that is ml square, and right hand side is a constant and that is also equal to ml square. Now the second expression which depends upon phi depends upon the variable phi is known to us. We have derived a solution for this second expression. Okay, where we have derived a solution for this second expression, the second equation is same as rotational motion in two-dimensional space. Okay, so in particular in a ring or in the last session we have solved the expression, we have solved this second differential expression. So what was the solution there? The solution had we had two linearly independent solutions. One is a plus e to the power iml phi, a minus e to the power iml phi. A is this normalization constant, and what was the value of normalization constant? The normalization constant was 1 over root over of 2 pi. So that was the normalization constant. We have derived a expression for normalization constant as well. So two linearly independent solutions are possible for the second expression. Now what was the when we applied the boundary condition, what was the values of ml that we obtained in during that expression, during the solution process? The ml values that we obtained was 0, plus or minus 1, plus or minus 2, and plus or minus 3. Here I have taken modulus, that's why I am not writing plus or minus, but actually ml values are 0, plus or minus 1, plus or minus 2, and plus or minus 3, like that it goes. So this is the solution for the second expression. Now what is the solution for first expression? We will not go into the detailed solution of first expression, rather we'll take the information from mathematics directly. It is important to note that the spherical harmonic function that depends upon phi, so the second expression is dependent upon phi, and when we solve this second expression we get a quantum number ml. So that's what it is written here, that depends upon phi is associated with quantum number ml. So what is the solution of the first expression? The solution of first expression will not be discussed, rather the results are summarized. Okay, we will not go into the solution of first expression, rather we will directly discuss the results of the first expression. And the second expression gives us quantum number ml. So what does the first expression gives us? We will see. Now we have to apply boundary conditions to first expressions also. So when boundary condition is applied to solve the both the expression, to ensure that the function, the spherical harmonic function is single valued and it depends upon theta and phi, when the boundary condition is applied, the boundary condition can only be satisfied when we take beta is equal to L into L plus 1. Again, L is a quantum number that we get after application of boundary condition. Now I am not going into the detailed derivation, rather we are directly focusing on the solutions. So the solution of the first expression is beta is equal to L into L plus 1. And what are the L values? The L values goes like 0, 1, 2, 3, like that. And from the second expression we have obtained ml values, and ml values are 0, plus or minus 1, plus or minus 3, like that. So I can also write ml is equal to minus L minus L minus 1 minus L minus 2, like that, and it goes up to L. So ml values are dependent upon L values, and it varies from minus L to plus L through 0. So these are the two expressions, quantum numbers that we obtained after the solution of both the expressions. So what are the quantum number? One quantum number is L and the other quantum number is ml. So note that L and ml are the two quantum numbers for 3-dimensional rigid rotor. In case of 2-dimensional rigid rotor, we got only ml, but in 3-dimensional rigid rotor, the problem depends upon two quantum numbers. One is L and the other one is ml. So as I said, the second expression is a function of only 5 variable, and it depends upon only one quantum number, that is ml. But the first expression depends upon two quantum numbers, and the quantum numbers are L and ml. Okay, so I can rewrite my spherical harmonics as the spherical harmonics depends upon two variables, theta and phi, is a product of two functions. One is theta function and the other one is phi function. The phi function is dependent only on one quantum number, that is ml, but the theta function is dependent upon two quantum numbers, and that is L and ml. Okay, so the theta function is depends upon two quantum number, and that is L and ml, and the phi function depends upon only one quantum number, that is ml. Okay, and ml values varies from -L to +L through 0. So there are total 2L plus 1 different values of ml. So suppose L is 2, L is equal to 2, then what will be the values of ml? The ml values will be -2, -1, 0, +1 and +2. So there will be 5 ml values. So for a particular value of L, there will be 2L plus 1 different values of ml ranging from -L to +L through 0. Now what are the energy eigenvalues? So what are the energy eigenvalues possible? Now we have defined beta is equal to 2 mu r0 square E over h bar square. Now mu r0 square is nothing but moment of inertia, and I will substitute that as I. So 2I E over h bar square. Now from the boundary conditions we have obtained beta is equal to L into L plus 1. So here when I substitute beta values, so what I am getting, my energy values I am getting, and energy is dependent upon L. So energy value, if I rearrange, I will get my energy value, and that goes like h bar square over 2I L into L plus 1. And what are the L values? L is a quantum number, and L values varies from 0, 1, 2, 3 like that. So the energy states are not continuous, rather they are discrete in nature, and the energy values depends upon the quantum number L. Okay, when quantum number L changes, the energy value will change. Okay, so similarly the eigenfunction, the spherical harmonic function must satisfy the eigenvalue equation. So if I substitute the spherical harmonic function, if I operate the spherical harmonic function on the Hamiltonian operator, Hamiltonian is total energy operator, the energy value that I am getting, the eigenvalue for energy I am getting is h bar square over 2I L into L plus 1. So when I operate the Hamiltonian operator on the spherical harmonics, I will get the eigenvalue, energy eigenvalue, and the same spherical harmonic function. Okay, so the energy eigenvalue that I am getting is h bar square over 2I L into L plus 1, and L values varies from 0 to 0, 1, 2, 3 like that. Note that the rotational energy values are quantized, and that once again the quantization arises through a boundary condition. Again, the discreteness of energy arises due to the imposition of boundary condition. That is, when we impose the boundary condition can only be satisfied when beta value is equal to L into L plus 1. We have not derived that expression, but we have directly summarized the conclusions. Now we will see the comparison between two-dimensional rotation and three-dimensional rotation, that is particle in a ring and particle on a sphere. So what is the origin of quantum number? The first question arises, what is the origin of quantum number in case of rotation in two-dimensional space and rotation in three-dimensional space? In case of two-dimensional space, there are two variables actually. One is r variable, that is the distance from the origin, and the other is phi variable, that is the azimuth angle. Okay, so but we have taken the distance from origin is constant, that is r is constant, and we have taken that r is r0. So only one variable is there. That's why the one variable, that is phi variable, angle phi variable, azimuth angle phi variable, will give rise to only one quantum number, and that quantum number is ml. So in case of rotation in two dimensional, we are getting the quantum number ml, whereas in rotation in three dimension, now what is the significance of quantum number ml and quantum number L? We'll study that in the next session. What is the significance of quantum number ml and quantum number L. Okay, now rotation in 3 dimension. Rotation in 3 dimension, there are 3 variables, that is this distance variable and the 2 angle variables. Again, we have taken the distance variable to be constant, so there are 2 variables, and 2 variables need 2 quantum numbers for the proper explanation, and the quantum numbers are ml and L. Okay, now what is the energy eigenvalue for rotation in 2 dimension? The energy eigenvalue EML is equal, that we have obtained in rotation in 2 dimension, is ml square h square over 2 mu r0 square. Mu r0 square is nothing but moment of inertia, so ml square h square over 2I. ml value varies from 0 plus or 1 plus or minus 2 plus or minus 3, like that. Here degeneracy is 2 for every level, where except for ml is equal to 0. When ml is equal to 0, the energy value becomes 0. Okay, now what is the energy eigenvalue for rotation in 3 dimensional space? The energy eigenvalue that we have obtained for rotation in 3 dimensional space is h bar square over 2I L into L plus 1. L values varies from 0, 1 to 3, like that. Now also we know that energy is given for rotational motion from classical mechanics, and we know that energy for rotational motion is given as L square over 2 mu r0 square. L square over 2 mu r0 square. What is L? L is the angular momentum quantum number. L is the angular momentum quantum number. Now the energy of rotation depends upon magnitude of angular momentum and its direction. Okay, so here in rotation in 3 dimension, the energy value that we have obtained, energy eigenvalue that we have obtained is h bar square over 2I L into L plus 1. Here this L is just a quantum number. Okay, but we also know that total energy is for rotational motion, the total energy is also given as L square over 2 mu r0 square, or 2I. Okay, so this the rotational energy is dependent upon the magnitude of angular momentum. Okay, so we will relate this angular momentum and energy terms. Now therefore there are 2L plus 1 total energy eigenvalues for same L values are possible, because for a particular L value there are 2L plus 1 energy values are there. So degeneracy of each energy level is 2L plus 1. Degeneracy of each energy level is 2L plus 1, and this energy level depends upon the angular momentum of the system. So with this I will stop here. Next session we will discuss about quantization of angular momentum. Thank you.